Okay, thanks very much. You probably wonder how we sort of manage we're constantly adding new things to Saxon, but occasionally when you're managing a code base that's now nearly 20 years old, you have to sort of look back at some of the old things in there and wonder what to do about them. And the background for this talk was that I have been slightly unconsciously uneasy about the fact that we've got this code in the product that's been there for 10 years to do document projection. And I was wondering whether anyone was using it and whether it was worth keeping, and also whether it actually had any relationship to the work we were doing with streaming. Originally, the idea was to common things up a bit, but that never happened. So I decided to take a little bit of a review of the document projection code in Saxon and think about what to do with it. This talk results. So what is XML projection? It's actually probably the best idea that anyone ever had in the whole of the history of XML technology. And hardly anyone knows about it. It was introduced in a paper by Amélie Barrien and Jérôme Simeon, apologies for my French, at VLDB in 2003, in an XQuery context. And the basic idea is that you take a query as input, and you look at what parts of the XML document are needed to satisfy that query, and then you build the document into a tree in memory, retaining only the parts of the document that the query is actually interested in. And it turns out for a lot of simple queries, the query is only interested in a very small part of the document. And if you build only that part of the tree in memory, then you've actually got an enormous memory saving and potential for a few other little savings as well. So that's the idea, and it works very effectively in theory, according to all the examples they did in their paper. And I decided it was about time to reinvestigate how well it worked in Saxon. So here's a schematic of how it works. You take the query, you do static analysis on it, and then in the normal course of events, the static analysis produces a compiled query. But in this case, the analysis has a second output, which is that it generates what in Saxon is called a path map, which is a map of all the paths in the document that are used by the query. And that path map is then used to filter. You inject a filter in between the XML parser and the tree builder, so that the events coming out of the parser are filtered, and only the ones that are relevant are used for building the tree. And you build a subset of the tree. And then you run the compiled query against that filtered tree, and if you've got the analysis right, the query produces exactly the same answer as it would have produced against the full document. So just to illustrate that another way, here's a trivial list of books. There's a query against a list of books. And the bits in red are the bits that the query actually needs. Now that looks like it's accessing quite a lot of the document, but that's because when we draw documents on PowerPoint slides, we like to simplify them. In the real world, a book list contains an awful lot more than 4 fields: title, author, date, and ISBN. It contains a whole host of stuff about history of reviews on Amazon and you name it. Entire publishing history of the book, what editions is it available, is it in, what's the price in every different country. You're going to have, a couple of kilobytes of data about each book in a real data file of this kind, and you're still going to run that same query that only needs those red bits. And so what you find is that in that kind of environment, the amount of data you need to keep to actually answer that query is a tiny fraction of the original, possibly only 2 or 3% of the original data. And so you've got an alternative to streaming. Instead of executing the query in streamed mode to save memory, you've got the option of stripping down the document to its bare essentials and only retaining the bits you need in order to save memory. In Saxon, document projection has been available since Saxon 9.0, in other words, it's pretty well since prehistory. It works in XQuery only, and there's a reason for that, and that's it's very hard to do this kind of static analysis in XSLT to work out which parts of the document are reachable. I was reminded this morning, in fact, I'd completely forgotten that when I put the path analysis into Saxon, it wasn't just motivated by doing document projection. It was also motivated by a project I was doing with Eric Boucher on Orbion. I don't think he calls it Orbion, he calls it Orbion, on the XForms product. And what you need for XForms is the ability to analyze which parts of a document are reached by each of the XPath rules in the XForms model, so that you know if there's been a change to the input, which rules do you need to evaluate. And so that's similar to the sort of schematron thing we were seeing this morning with dynamic re-evaluation of rules. If you can work out which rules are affected by which changes to a document, then you can work out which needs to be re-evaluated. And that path analysis of basically reachability analysis, which parts of the document are accessed by an XPath expression, turned out to be very much the same analysis as is needed for document projection. So it's not widely used, and I know it's not widely used because I tried it a few weeks ago and I found it didn't work. At least, you know, we've got half a dozen tests that we've been running every release for 10 years, and those tests work. But when you try and do something other than those tests, you quickly find it's broken. And one of the main reasons it's broken is that it hasn't been updated for the 3.0 specs. So we just aren't doing all the path analysis for a lot of the new constructs. So that's pretty good evidence that no one's using it, which is a shame, because I hope to show it's actually quite a powerful technique. And when we started doing the streaming work, I had good hopes that the path analysis used for document projection would have a lot in common with the analysis you need to do for streaming. In fact, I think it inspired a lot of the analysis that went into the spec, but it ended up being sufficiently different that the actual logic in the code is completely different. Let's take a little look at it working in practice. You don't want to see more slides. So here's a query from the XMark benchmark. The original VLDB paper uses the XMark benchmark queries and shows their effect on projection. It's written the way all the XMark queries are, as a flower expression. I think most people nowadays would write it as an XPath expression. But it's saying for, I won't go into what the actual data structure is. It's actually quite complex. But it's saying, find all the persons with that particular ID and return their name. And I'm running this against the 100 megabyte version of the XMark database. And I'm running each query 10 times to get decent repeatable performance numbers. And if we run that on 100 megabytes of input, let's take a little bit of a look at that. So we're building, first of all, we're analyzing the query, and it's going to say somewhere what the analysis time is there. That's not a very meaningful number because it's actually dominated by Java VM warm-up time. It's probably really more like sort of 250 or 300 milliseconds just to parse and compile that query, which seems an awful lot. We are then building the tree. This is running without document projection or streaming or anything. We're then building the tree, which is taking 1.4 seconds. And we're then running the query. And we're running it repeatedly. And the first time we run it, it actually takes 48 milliseconds. And then on subsequent runs, it takes about 0.1 milliseconds. Now, I had a sort of panic this morning. I thought, surely it can't really be running in 0.1 milliseconds, searching 100 megabytes of data. And I had an inspiration and realized that actually this method of running the query repeatedly, we encourage people to do it to get repeatable numbers and to discount the effect of warm-up time in the Java VM. But actually, it's having another completely spurious effect in this case. So these numbers are a complete cheat. What's happening is that the first time you run the query, the optimizer has said, that's a handy thing to have an index for. And so the first time you run the query, it builds an index on people by ID. And that's what's taking 50 milliseconds. And then all the subsequent queries, it just looks up that index, and that's what's taking 0.1 milliseconds. So it's not actually searching 100 megabytes in that time. It's actually just looking up the index that it built the first time round. This is why performance is so magic. There are just so many ways of getting wrong numbers and of being deceived by your own figures into thinking that you've proved something that you haven't. But it's still not bad. 50 milliseconds still is the actual execution time for the query is vastly faster than the time for building the tree. It's even faster than the time for compiling and analyzing the query. So this kind of thing shows that actually an awful lot of the work we've done in the last 10 years to make queries go as fast as possible, is actually wasted effort in some scenarios, and in particular in the effort where you're compiling the query every time you run it. We're putting an awful lot of effort in at compile time to make the runtime faster in ways which even against 100 megabytes is actually not justified. So that's it run without projection. If I run, I'll just pin that so we can look back at it and run it now with projection. So all we have to do is add the option minus projection, remembering that it's possible to type on a keyboard when you're standing up. So one thing you never practice, isn't it? You know, when you're doing a presentation, what's it going to be like if I'm standing? Okay, so that's run again. The analysis time is still, 400 and something milliseconds. It's giving some feedback on the use of document projection, and it's reporting a 98% reduction in the number of nodes in the tree that it's had to retain. So what that means in practice is that if you had a limit of, let's say, a gigabyte on the size of document you can practically process without streaming or projection, then projection has a good chance of raising that limit by a factor of 100. So you might not even need streaming to get the memory reduction that you need to fit this query into memory. The the tree building time is reduced a bit. You remember it was sort of 1.4 seconds before, it's now 1.0. The parsing time is exactly the same. I think this 100 megabyte document takes about, it would take about 900 milliseconds just to parse it and do nothing else. By the time you add some tree building at the back of the parser, it takes a bit longer. And what's happening is by building less of a tree, we're saving some of the work. And so that's cutting the tree building time from 1.4 to 1.0. And that's actually the biggest effect on runtime here, is that it's reducing the tree building cost. The execution time of the query is much the same, a little bit faster, from 50 milliseconds down to 4 to 6. And again, these numbers are just using the index, which, as before, is pretty spurious. So that's projection in practice. And it works on all the queries in the XMark benchmark. And actually, most of them it is achieving a reduction of about that amount, a reduction to better than 95% in the size of the data that's needed to run the query. So benefits of document projection, you don't need to change the query at all. There are none of these sort of streamability rules that say you can't have multiple downward selections and you can't have joins and you can't have reordering. You can use any query that you like. The more complex the query becomes and the more of the data that it accesses, the less the benefits will be. But it's very incremental. There's no sort of cut-off point where you can say, for this query, it's just not worth doing. So it's quite a soft and adaptable technology in that sense compared with streaming. And the potentials for memory savings are quite extensive. What are the limitations? Some of them are the same as the limitations for streaming, which is that it only applies to single-shot queries. If you want to use the document in memory for more than one thing, then you're out of luck, because this is very much customizing the in-memory representation to one query. The one reservation for that is that if you want to do the same query lots of times with different parameters, then streaming doesn't help you, but projection does. Because the projection rules are the same regardless what the values of the parameters are. So the projected document can be used to answer the same query with different parameter values. There are things that you can't statically analyze, especially lots of things in 3.0. Dynamic function calls, any kind of eval. You can't apply this to XSLT because of template rules, which mean you can't do the reachability analysis. So it's not easily going to apply outside that domain of fairly simple XQuery execution. So this is just a slide giving that information. So 50 milliseconds isn't bad, but it's not quite as good as I thought. I don't know if the wrong figure found its way into the paper. It might well have done. So looking at the queries across the whole, I already mentioned that 19 of the queries achieve memory reduction of 95% or better. The results Saxon is achieving are very consistent with the ones that Marianne and Simeon reported. The query analysis cost is not measurable. There's no measurable extra cost on the query compilation time. Tree building time about 25% better. Query execution time a very small amount better, but that's not why you do it. So let's compare and contrast that with streaming technology. Streaming is defined in the XSLT 3.0 candidate recommendation of last Tuesday. Hooray. But in Saxon, there's also a subset of streaming capability available in XQuery. Either through an extension function called Saxon Stream or through a -stream option on the XQuery command line. And that just rides on the back of all the streaming work in XSLT. And I'm going to be showing a few query examples just so that we can compare them with document projection. Let's look at the one we've been looking at with streaming. And I will do a deliberate mistake here, first of all. So let's run that query with -stream and see what happens. And it says streaming is not possible. The expression bound to the variable $B is not grounded. And is not grounded basically means the value of the variable contains a streamed node. And one of the rules of streaming is that you can't bind streamed nodes to variables. So it's telling you no luck on that one. Can't do it. But fortunately, there's a very simple change you can make to the query, which is to write it the way any sane person would have written it in the first place. as an XPath expression. And if we change to do it that way, I'm running it 10 times, remember, and this time it's actually processing the whole file 10 times, because that's the nature of streaming. So, analysis time, not very different from what we had before, no reason why it should be. And it's now processing the query in streamed mode, and the execution time, it starts off at 1.6, and then after I've run it a few times, it drops to about 850 milliseconds. So basically, the execution time for the query is dropping to essentially the parse time of the file. The time is dominated by the XML parser time of actually parsing the input. The query execution adds only a negligible amount to that. This is 100 megabytes of input, and we can see that the memory usage is well down. Obviously, it's variable. It's depending on what the garbage collector is doing at the time. But it's running in a few tens of megabytes because it's basically not got any space allocated to the document tree. That compares with putting a full 100 megabyte in tree, which is going to take 500 megabytes of memory to hold the internal tree representation. So the streaming is working there. What's the difference? Answer is we had to modify the query. We can't stream any query. We have to stick to certain rules. Sometimes the changes are more extensive than that. For example, here's one of the queries in XMark, that's Q4. That's looking at all the open auctions and saying if person 18829 was a bidder in that auction earlier than person 10487, the double left arrow there is a test for whether two nodes are in document order. So this is testing whether both those nodes exist and are in that order among the siblings of the person ref elements. Well, that's not streamable because you're making two downward selections. If I try to run that query in streaming mode, then I get this kind of error message. And really, giving people decent error messages for streaming is really one of the tough challenges. Because the rules in the spec are so complex, you can't expect people to actually understand the rules in the spec. They are dreadful. But yet, at the same time, you want to give information that can be a little bit related to the way the spec describes the constraints. So I've tried quite hard to make the rules understandable by mere mortals, but yet at the same time comprehensible in terms of the rules of the spec to people who know a little bit more about what those rules are. So tell me if you think I've done a good job, and I'll try and improve it. But what it says is there's more than one consuming operand. This is what they are, the two bidder expressions on line 5 and 6. So you're not allowed more than one consuming operand. That means the predicate isn't motionless. And in addition, the expression bound to variable b is not grounded, so there's another reason it's not streamable. So when you fix those problems, again, it turns out to be quite easy to fix them. You can end up with an expression like this. And it's done the magic fix for all such problems, which is to use copy of. What copy of does is it takes a streamed node in the input and says, at this point, I'm going to materialize the tree underneath that. And so you've got to allocate memory explicitly to that subtree. So it's allocating memory to the subtree under every open auction element. And once you've once you've materialized that subtree, you can then do arbitrary navigation within that subtree, and you're then unconstrained as to what kind of code you can write. So it's a general fix for a vast majority of streaming problems. Of course, it only works if the subtree under an open auction is small enough to fit within the amount of memory that you've got. Because what it's going to do is to populate that subtree for one open auction, and then when you get to the next one, it's going to garbage collect that and use memory for the next one, and so on. It's sometimes called burst mode streaming, where you sort of build one subtree, process it, then you throw it away and build the next one, and so on, moving through the tree in bursts. So this one will stream. We won't bother with the repeat this time. So there it is. So it runs in streaming mode. I've shown the same queries running with streaming and projection. Let's compare them a little bit. Whoops, what have I done? How does streaming work? Like document projection, we start with static analysis. So we have to do some analysis of the code and work out whether it's streamable or not. If it is streamable, then you're not going to build a source tree. You're going to execute the XQuery or XSLT or whatever it is directly on the data coming from the parser of a stream of events. And that's only possible in layman's terms. In intuitive terms, it's only possible if you process the data in exactly the order that it arrives. So if your query is somehow sort of isomorphic, if the data it accesses is isomorphic with the data that's coming, the stream of events coming from the parser, then it turns out to be streamable, and if it's not, which means if you're doing joins or sorting or anything like that, then it's not going to be streamable. If you find that the data isn't streamable, then really there's two strategies you can adopt. You can fall back to non-streamed processing, or you can reject the query. And Saxon's got sort of modes of operation where you can choose either of those options. So streaming in Saxon's been developing over quite a series of releases, as the XSLT spec in particular has developed. And I spoke here, I think it's 3 years ago now, about the internals of the implementation, which does everything in push mode. So events are coming from the parser in push mode. Here's the parser pushing the events along the pipeline. If you're schema aware, you've then got a push mode validator, which is validating a stream of events in push mode. And what push mode means is that the supplier of data is invoking the consumer. So if I'm the parser, I'm telling you when data is available, and you are then reacting to that data becoming available. Whereas pull mode says the consumer of data is in control and tells the supplier of data, give me some more. So this is supply-driven rather than demand-driven. The streaming XPath engine pushes the events along to the transformation engine, the XSLT. There can be another validation path out here, and finally you push events to the result tree. And the result tree itself isn't a tree. It's bypassed. The result events are pushed directly to the serializer, which outputs them as lexical XML. So that's the architecture of the streaming code in Saxon. So what we find when we do all the XMark queries, firstly, we need to rewrite the queries to make them streamable. When we do that, 14 out of the 20 queries turn out to be streamable. 5 of them aren't streamable because they use joins, and joins intrinsically sort of navigate all over the input data and therefore can't be streamed. 1 of them isn't streamable because it uses sorting. And the query execution time is typically around 900 milliseconds, and that's basically the time taken to, to, 100 megabytes of data. 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 100 megabytes before we look at this comparison chart, let's just look at another example, if we can, quickly. This time is data that really needs to be streamed. So I've got a file of addresses here, and this is 2.6 gigabytes. So processing 2.6 gigabytes gets a little bit difficult. If you try to process it raw, this is what's going to happen. Yeah, let's just do that query there. .6 gigabytes, remember, this time. And we run out of steam. Or rather, we run out of heap space. So I'm sure you've all seen that at some stage in your careers. Just too big to handle in heap space. To handle 2.6 gigabytes of source data in the full tree representation would need sort of, I reckon, rule of thumb 5 times, 12.5 gigabytes of heap space in the Java VM. We're starting to hit problems about the actual 2 gigabyte addressing limit in strings and arrays in Java. I don't know who's going to solve that problem for us. But it's raw heap space here. We can solve that problem by streaming. If I just add minus stream there. Right, and the first thing to notice here is that the first bit of data came out very quickly, because it's actually processing the data as it arrives. The query asked for the first record in the input, and as soon as it finds the first record, it can output it. So you're not just reducing memory, you're also reducing latency, if that's important in your application area. This should actually then early exit, but actually it's processing the whole file. And I think that's a limitation of the XQuery streaming as distinct from the XSLT streaming, but it's not quite so good as doing early exit. Because this could have decided at that point that there wasn't going to be any more data and it could stop, which means it doesn't parse the whole input file, which means that actually if there's any errors in the input file, you'll never know about them. So execution time, 27 seconds for that. That seems to be fairly typical, 10 seconds for a gigabyte seems to be the sort of rate you can expect to get when you're doing streamed processing. And again, that's basically the rate at which you're parsing the data. See if this one works with projection. Any guesses? No? Well, the answer is there's not very much it can filter out, is there? When you're doing /*/*, it needs all the data, and so it's probably going to fail in the same way. Yeah. But it turns out if we do a different query, like let's try exists // city. Then I think that one's probably going to work with projection. So we're just at the margin of what's feasible here in terms of actually fitting things within memory. The query execution time should be about the same. It'll still dominated by the parsing time. So about 30 seconds, I would expect. Yeah, so that one's worked. But what we'll see is that it used a pretty fantastic amount of memory. 1.5 gig of memory there. Despite the fact that it achieves an 89% reduction, apparently, in the number of nodes it was holding in memory. So let's sum up. If we compare the two techniques, they both rely on static reachability analysis. But there's a difference in the analysis in that on the projection side, the answer is never going to be no. The answer is going to be the level of filtration that you get on the input. That's what's going to vary, not a Boolean yes or no answer. Both of them really rely on this scenario that you're reading the document once for every query execution. So they don't work for the sort of lookup document that you read at the start of the day and then keep using for looking up exchange rates every time you do a transaction for the course of the day. It's not that kind of scenario at all. Streaming gives you constant memory, even for infinite documents. So however big the document gets, you are never going to run out of memory. You can process streams of data from satellites or from telemetry using streaming. With projection, you're getting a linear reduction in the amount of memory, but at some stage you are still going to run out. But the big advantage of projection is that it's still very useful on non-linear queries. So queries like sorting or joins, you can still get a very, very big saving on those using document projection, so long as they're only using a small amount of the data in the file. And so that's really the big plus point. That is why we shouldn't throw out projection out of the Saxon product, because it is performing a useful service that streaming can't do in terms of a style of processing very large documents that are too big to fit in memory in a way that streaming can't actually handle. And then the other one is early exit. It didn't work as well as I would have liked on some of those examples, but there are a lot of queries, and it certainly does work in a lot of cases in XSLT, where if you can get the answer from the beginning of the file, then you can stop. You don't need to read the rest. And there are a lot of queries where you only need to know what's in the header of the file. You need some metadata that's at the beginning. And that's a really big plus. If you just want to extract that metadata, read it, and then carry on, you don't actually have to parse the whole file. So that's a big use case for streaming. So I think there's lots of opportunities. The static analysis algorithms used by streaming and projection can certainly take advantage of each other. We could improve reuse there. I think the stuff we do for projection could actually be used to automate some of that injection of a copy of. I think we can detect a lot of the cases where that's needed and inject it automatically, and I think that's an option we should look at putting in to make more queries streamable. Projection handles variables and streaming doesn't, and there's no reason for that. It's just a limitation in the analysis. I won't talk about functions, but there's problems with both. So that's it. Questions?
What about performance when doing the streaming on efficient XML? Because you say that the parsing is most of the time. Did you do any tests on that?
I'm sorry, the question is?
what about performance when doing streaming on efficient XML, or binary
Oh, efficient
XML?
XML. Yeah, I mean, it's orthogonal. If we can speed up the parser, then we can get benefits from that. And efficient XML, binary XML might well be one of the ways of doing that. But yes, I think people don't realize the extent to which transformation is dominated by parsing cost in very many cases. And we definitely should be putting more effort into cutting down the parsing cost for a lot of these workloads. And that might well be one of the ways of doing it. Yeah, thanks.
Michael, I would like to know how you think about the following alternative. The projection you describe is driven by the query. So why not let the query author, when parsing the document, let explicitly determine how projection is done? So I'm thinking of a new function, could be called filtered minus doc, with two parameters, a URI and a specification where you say what you want and what you do not want.
Mm. Yeah, there's actually a function that was added to XQuery called unordered, with that sort of motivation in mind, that it's a sort of declarative way of saying I don't care about the order of the results. Of course, no one uses it. And there's one of my first rules with performance is that if you add a knob that people can turn, then only 1% of the user base will ever discover it exists. And so performance features that involve twiddling knobs to improve performance are always a little bit frustrating in that people don't know how to twiddle them. And the existing unordered feature in XQuery is one example of that. Yes, there are things you can do with annotation, and of course with streaming we're doing that as well to an extent. Sorry, have I misunderstood the question?
It seems to me you misunderstood me. I mean, it is so clear, so explicit. For example, I would like to have the possibility to say doc of a URI, but I only want the root element with its attributes as the simplest possible case. So I can imagine very well to think about how to specify. Very simple, for example, you can give qualified names of elements you want to skip and so on. It is very explicit, very clear. I do not understand why you compare this with ordered, unordered. I mean, my experience is I know the documents I'm working with, and I know all the rubbish I'm not at all interested in. I would love to be capable of saying right away, this part I don't want. And I think this is simple. Yeah,
well, I'm hoping one of the things in the sort of conclusions, things we might be able to do, is to improve the analysis on XSL source document, so that we can detect cases with XSL source document where you can detect that this sort of projection is possible and do it automatically. Because, I mean, going back to what I was saying in response to your question, the reason no one uses projection is that it's one of these knobs you can twiddle that most people don't know about. And my aspiration is to find a way of using these technologies in a way that spring into action without you asking for them, just because we're smart enough to know when it's needed.
Okay, thank you very much. Probably we don't have time for any additional questions now, but you can continue after today during the social event, because it's very interesting and very in-depth topic. So thank you again.
Thank you.